Yeah, in today's class, we talk about the data hazards. So in this data hazards, why these data hazards are there and why these data hazards are happening, that we talk in today's lecture mostly. And then uh, these data hazards occurs when the current instruction requires the result of a preceding instruction, but there are insufficient segments in the pipeline to compute the result and write it back to the register file in time for the current instruction to read that result from the register file. So we typically remedy this problem in one of three ways. We call, one we can call that, forwarding. And second, we call code reordering. And third, we use the stall insertions. So these are, three different, the remedies will be used to come out of these data hazards. So in forwarding means in order to resolve a dependency, one adds a special circuitry to the pipeline that is comprised of wires and switches with which one forward or transmit the desired value to the pipeline segment that needs that value for computation. Although this adds the hardware and control circuits, the method works because it takes far less time for the required value to travel through the wire than it does for a pipeline segment to compute its result. Whereas in the code reordering means here the compiler reorder segments in the source code or the assembler reorder object code to place one or more statements between the current instruction and the instruction in which the required operand was computed as a result. This requires an intelligent compiler or assembler which must have detailed information about the structure and timing of a pipeline on which the data hazard would occur. So we call this type of software as your hardware dependency compiler. And talk about these insertion means it is possible to insert one or more stalls, that is no the operation instructions into the pipeline, so which delays the execution of current instruction until the required operand is written to the register file. So this three is which is contrary to the pipeline process design. Stalls are an method of last resort that can be used when compiler action or forwarding fails or supported in the hardware software design. So this is it okay? The voice is okay now? Just give me a second. Is it fine now? The audio internet is not static. Is it clear now? Okay, okay. That's great. Okay, so as we talk about this data hazards, says that the data hazards, when an instruction depends on the result of a previous instruction, that exposes overlapping of your instructions. So, as said, there are three types of data hazards, or we can call them as uh, the data dependencies. Data dependencies. One is read after write data hazard or data dependency, or we call this as your true data dependency also. And the second data hazard, we called it, write after read, right after read, or we call this as also your anti-dependency, your anti no dependency. And third one, right after right, we call this as your output dependency. Output dependency. So what is there in this read after write, data hazard? Read after write means, the first instruction will write after reading X. After reading X, read X, then you write. For example, if you take the instruction, suppose if I have two instructions like instruction 1 and instruction 2, if the instruction 1 says that R2 is equal to your R2 plus your R3, and if I have the second instruction like your R5 is equal to your R2 plus your R4. In that case, first it computes this one. It writes into your R2. The result will write into your R2, and then that will use for, after writing, it will use for your the read. So here the read operation performs. Here the write operation performs. So we call read after write. Read after write dependency. And second one is write after read, or we also call it as your anti-dependency. Anti-dependency. So here first read X value, and then write into your X. Read X value after write into your X. So that says your write X after write X. Your write X after read X. Read X. This is, or in terms of instruction, let me take if I have two instructions like instruction 1 and instruction 2. If I have the instruction 1 say R1 is equal to your R2 plus your R3, and another instruction is suppose your R2 is equal to your R4 plus your R5. In that case, here the write operation is happening, and here is your read operation is happening with the register 2. So in that case, it says first, write after read. So write after read means first read, read operation is happening after, write is happening. So we call this as your write after read, right after read. And the third case, the third dependency is your write after write. So write after write means write the first write into your X and write into your Y. Another instruction X here. So then we called it as your write after write. So if you see the example like for instruction 1 and instruction 2 for write after write, if you see suppose if the instructions are like R3 is equal to your R1 plus your R2, and R3 is equal to your R4 plus your R5. In that case, the first instruction, this will be computed and write into R3, and the next instruction when it is executed, then whatever value is there in R3 that will be overwritten. That is again write into R3. But what is the problem comes here? Sometimes if this R3 operands R1 and R2, if they are depending on some other instruction, in that case, this instruction may stop for a period of time and this instruction may execute. In that case, the value of R3 will overwrite in the instruction your R1. So that will another dependency, or we call this your write hazards, data hazards. So when you are dealing with the data, when you are dealing with the data during the execution, so there are three types of data hazards that we find. One is read after write, and write after read, and your write after write. So generally, in write after read, when it happens, this write after read generally happens with your program counter. As we know that as soon as the program counter issues the address to your instruction memory, and if that instruction is fetched from the memory, the program counter automatically increase. Auto increment will be done, program counter plus your 4 bytes, right? So write after the read. Once the instruction is read, write into your the program counter. So that happens, right? So let us see these with an examples and how these hazards will be handled in the pipelining execution. For example, if you have the instructions given to us, if there are 4 instructions, the instructions are the are add instructions, and from this instruction, it is clear that add R2 with your R1 and store the result into your R3. So when the second instruction is going to execute in this pipeline, the first operand or source operand is read after writing this register R3 in the instruction 1. Similarly, in the instruction 3, the register R3 that reads the data from your R3 after writing the data into your R3. The same way, the instruction in the instruction 4, the R3 register will be read after writing the value of your R2 plus R1 into your R3. So there is a read after write data hazard is there in this instruction. Then how these instructions are going to be executed? How these instructions are going to be executed? So in the structural hazard, we have seen that how instructions are utilizing the functional units. So we know that in the instruction fetch, the functional units which are used, one is your program counter, your instruction memory, and your adder, which is used to add PC plus 4 bytes. Similarly, in instruction decoding phase, it will use the register file. Register file functional unit is used. So in the register file functional unit, what is happening? Whatever the cycle is there, in that instruction, first half cycle is used for writing the data, and second half cycle is used for your read the data. Okay. And similarly, in the structural hazard, we have seen that to differentiate the memory which is utilizing in the instruction fetching and the memory which is utilizing at the memory execution. In the memory execution, that is differentiated as the memory which is in the memory stage or memory sector. We call that as your data memory. So in data memory part also, first half is used for write, second is for read purpose. Now let us see in this execution when the instruction 1 is going to it first in the first cycle, it is to execute first cycle instruction memory. In the second, uh, in cycle 1, instruction fetching, which is getting the instruction memory. From this instruction memory, the first instruction is executed. In the second cycle, okay, the first half part is used for your writing purpose, and second half for in instruction decoding. In instruction decoding, the data is read. The data will be read. In the third cycle, it is going to the execution part. You are executing, and in the fourth cycle, it goes for your memory. The memory. So here, the which memory is using? The data memory is using. Okay. In the fifth cycle, it go for your write back. Okay. So in this case, if you see that when the first instruction is fetched and decoded, then it goes to execution. And when the result will go and write into your R3 means after fifth cycle. But if you see that in the first cycle, instruction fetching done, instruction decoding done. In the second cycle, 1, 2, then execution done. In the third cycle, then in the fourth cycle, your memory access will be done. In the fifth cycle, the write back will be done for the instruction 1. So the instruction 2, your instruction in the second cycle, your first instruction is in instruction decode stage, so instruction fetching is idle. So in the second cycle, second instruction will be taken. In the third cycle, the second instruction will go for your instruction decoding. But in the instruction decoding, the second instruction is required the value which is there in R3. But at this third cycle, instruction 1 is not yet completed. So this in the second cycle, it will stop it will stop the execution. Means it will not allow this second instruction to get into the next stage, that is your execution stage, because the value is not yet ready. So after fifth cycle half part, the value in R3 is ready with the value, from your register file. So the instruction 1 writes R3 in cycle 5. However, instruction 2 needs R3 in cycle 3, because when it is decoding, it requires the value in cycle 3. And instruction 3 needs this R3 in cycle 4 for execution. Right? So before the latest value, which is R3, is not written, then that happens. It has to be, gives some kind of problem. Because if the value is not written in the instruction decoding, if it takes R3 value, then that R3 is, if it reads the R3 instruction 2, that is a wrong value, okay, which is not updated at this level. And similarly, for instruction 3 also, when it is entering into the instruction decoding phase, here also it is in the fourth cycle, but still the R3 value is not updated. So the R3 which is read for instruction 3, that will also gives your R3 wrong value, incorrect value. But whereas for instruction 4, when instruction 4 is fetching in the fourth cycle and decoding in the fifth cycle. That is the when the half of the cycle part in the fifth cycle, it is reading the value of your R3. So here R3 gives the correct value, correct value, correct value. So the data hazards, they read after write data hazard happens with your instruction 2 and your instruction 3, but not for instruction 4. As said, the instruction 4 reads R3 at the second half of your cycle, second half of your, the cycle uh, uh, 5. So therefore, there is no data hazard for your instruction 4. So how to handle these problems then? So when R3 is written back in cycle 5 and much later than when the instruction 2 and instruction 3 need it, then they provide this wrong value. So how to handle this? This we call your, read after write data hazard. So what are the solution for this? So the solution for this data hazard is, before solving the read after write hazard, pipeline needs to be able to identify the data dependency that cause the read after write hazards. So the hardware component for detecting data hazards is called your pipeline interlock. Pipeline interlock, a separate hardware will be used. So in this pipeline interlock, it needs to keep register ID. In our example, in this case, it is depending on your R3. It needs to keep the register ID along with the pipeline stage. This register ID is going to be right back in the pipeline stage. That is your write back stage, and use that the comparator to check for the hazards. Check for the hazards. So the first solution for your read after write, we call your stall the pipeline. Stall pipeline. This is the simplest one and the universal solution for your read after write hazard solutions. So what it do in this case? Let us see in step by step. In the first instruction, in the first cycle, the your instruction 1 goes into your fetching, instruction fetching. In the second cycle, it will do the the instruction decoding. In the third cycle, it will execute, and in the fourth cycle, the memory write will be there. In the fifth cycle, it go for your write back. Okay, so these stages happen with the instruction 1. Now see, for instruction 2, if we take, in the first cycle, the instruction fetching is busy with your instruction 1, so the instruction 2 will not taken. In the second cycle, instruction 1 entered into your next stage, that is instruction decoding. So instruction fetching functional units are free, so that will allot your instruction 2. Okay, in the third cycle, your second instruction enters into the next stage, that is your instruction decoding stage. In this instruction decoding stage, when it enters, then in the third cycle, your instruction fetching and instruction fetching, what you call the for instruction 3, the instruction fetching stage is idle. Instruction fetching, because in the third cycle, first instruction is in execution stage, second instruction is in instruction decode stage, so it is free for your instruction 3rd, right? So then at this stage, if you see, at this stage for instruction 3, When instruction 2 is supposed to decode, it requires the value of your R2. It requires the value of your R2. Okay, but that R2 is not at, sorry, R3 is not at right. So that is in the write back stage. Write back stage. In that case, this ID is going to be this ID. The second instruction. The second instruction is not forwarded to the next. Is not forwarded to the next stage. So there it is going to stop the execution of the second instruction at at this stage, because the ID in instruction decoding, it requires R3 value. It requires your R3 value, updated R3 value from your instruction 1, which is not yet completed the instruction, because at this cycle 3 instruction is simply executed, but the value is not right back instruction 3 here. So it stalls that one. So what about instruction 3? In instruction 3, it is in instruction fetching stage, but if it is tried to go into the next cycle, that is instruction 2, the cycle 2. In that cycle 2, already instruction 2 is there, which is already utilizing the services of your instruction decoding phase. So automatically your instruction 3 will also stop or stalls. Okay, so stop the instruction from executing this. Okay, so then in the fourth stage, both the second and third instructions are stopped. Okay, now what about the fourth instruction here, the instruction 4? The instruction 4 cannot be entered into your the first stage of your pipeline execution, because the instruction fetching is busy with your instruction 3rd. So at the fifth stage, okay, the first half part of your fifth stage, is your write back. That write back writes the result into your R3. So this stall is continues up to the first half stage. So in the second half stage, the R3 is ready. R3 is ready with the data. So then the instruction decoding will start executing from here. Instruction decoding will start, means the second half it will get the instruction decoding, and then at the sixth stage, your instruction 2 will enter into your execution mode. Because in instruction 5, in cycle 5, first instruction writes the result into your R3. So in the second half cycle, instruction 2 reads the data from R3. So then in the sixth cycle, your instruction 2 will enter into the execution phase. Okay, so then in this cycle, when this instruction decoding is finished, then your instruction fetching, the third instruction is still in start. When the second instruction at sixth cycle entered into the execution mode, then your third instruction get into your instruction decoding phase. When this is in the instruction decoding phase, third instruction is in instruction decoding phase, then your first instruction fetch, first stage become free. When first stage become free, your fourth instruction will enter into your instruction fetching in the sixth cycle. Then in the seventh cycle, if you see in the seventh cycle, your second instruction will enter into your memory access mode, then this execution stage will become idle. So your third instruction will enter into the execution mode. Your execution mode. When the third one is getting to the execution cycle, then your fourth instruction will enter into your instruction decoding. Will enter into the instruction decoding. Right? Then in the eighth cycle, your second instruction will enter into the last stage, that is write back. When it is enter into write back stage, your instruction 3 will get the opportunity to get into your memory stage. Okay. When this third instruction get into memory stage, your fourth instruction can get into the execution stage, execution cycle. Okay. So then in the ninth cycle, your second instruction is finished. Your third instruction will entered into it goes to the next stage. That next stage is the write back stage. And at this stage, when this third one entered into your write back stage, your fourth instruction will get into the next stage after execution. It will get into your memory access stage. So your third instruction finish in ninth cycle. In 10th cycle, your fourth instruction get into your write back stage. The write back stage. So this is the way of executing the instructions when there is a dependency, or we call true dependency. So if you see here in the first cycle, first instruction is entered. In the second cycle, your first instruction entered into your the ID stage, and your second instruction enters into your instruction fetching stage. In the third cycle, your first instruction enters into the execution stage, because as we know, let me just recall you the diagrams. Third stage, fourth stage, and your fifth stage. In the first cycle, for the first cycle, only instruction 1 will be there. So this cycle is busy. Okay, called cycle 1, cycle 2, cycle 3, cycle 4, cycle 5. In the second cycle, it is moving into the next stage, that is your instruction fetching, instruction decoding, execution, memory, and your write back. So in the second cycle, it is more into the instruction decoding, and when it is shifted, then the instruction 2 will be enter into your instruction fetching, because it become idle now. So then in the third cycle, your instruction 1 move into your execution, your instruction 2 is entering into your the instruction decoding phase. In the instruction and decoding phase, it requires the R3 value. It requires the R3 value, which is not yet executed by your instruction 1. So here at this stage, your instruction 2 stops. At this stage, your instruction 2 stops. Stop executing. We call that as your stall the pipeline. Then from here, your instruction 1 goes to your memory access. From there, it goes to your the instruction 1. It goes to your write back. So there, your R3 value will be ready. That R3 value will be given to your in the instruction decoding. Then it will enter into this one. So at this stage, At this stage, ID is busy with your instruction 2, but your instruction fetching is idle. So here the I3 is entering. So that's stopping process. We call it as your bubbling, or we call this as your bubbling, or we can write it as your no the stalling process also, right? So now suppose if I have, let me give you one instruction 1, instruction 2, instruction 3, your instruction 4, okay, and the instructions given as your add your R3, it stores your R1 and R2 a calculated value. Your add your R4, your R5, sorry, R3 and your R5. Next, another instruction is your R6, here R7, R8, add your R9, R10, R11. So to execute these instructions, you are definitely finding a read after write hazard is there. But by using stalling, how many cycles these instructions will take to execute? Can you please do this and give the type the result in the chat box? Use the given 4 instructions. Use the given 4 instructions and execute the read after write hazard solution, and tell me in how many cycles these 4 instructions will execute. Do the exercise and give the answer in the chat box. There will be only one answer. How many cycles does these four instructions takes to execute? There are 52 students are there. I expect answer from everyone, whether it is right or wrong. So your answers are recorded. Whether it is right or wrong, it doesn't matter. The correct answer is 8. The correct answer is 8 cycles because we have only two dependencies here. No, only first and second instructions they are having the read after write dependencies. The next two instructions are not depending. So let us see that. Let me write it for you from here. For the first instruction, for the instruction 1, I can simply write the numbers here 1, 2, 3, 4 instruction. Instruction 1, in cycle 1, it goes into instruction fetching. In cycle 2, instruction decoding. In cycle 3, it entered into your execution. In cycle 4, the memory access will be done. And in cycle 5, it go for write back. Now see, in the second cycle, second instruction, the second instruction will be taken and that will assign the first instruction is busy with instruction decode. So instruction fetching is free. So that instruction fetching allotted to your instruction 2. Okay. Then in the third cycle, your instruction 2 enters into your instruction decoding phase and your third instruction enters into this instruction fetching will idle, so it will enter into your instruction fetching. So in the second cycle, instruction decoding. In the instruction decoding, second instruction R3 is read after writing into R3 in the instruction 1. So here it becomes stall. Okay. And in write back stage also, it wait until it write, that is stall. So third instruction will be, the third instruction is busy with your, in the instruction fetching, but the second instruction is busy with ID, so it will not allow instruction 3 into your instruction decoding, so automatically it also stalls. Automatically it also stalls until your instruction decoding become ID. So he automatically for fourth, the instruction fetching stage is busy with your instruction 3, so it stops. So at cycle 6, your second instruction enters into your execution. Then your instruction 3 enters into your instruction decoding. Right? So then your fourth instruction is allowed at your cycle 6 into your instruction fetching. So in the seventh cycle, your second instruction get into your memory. Your third cycle, in the third instruction get into the execution mode. And your fourth instruction get into instruction decoding. get into instruction decoding. Then in the eighth cycle, your instruction 2 goes into write back stage. Then instruction 3 goes into your memory. Your instruction 4 entered into your execution. Then in the ninth cycle, your third instruction get into your write back. Your fourth instruction get into the memory access, and in the 10th cycle, your fourth instruction will get into your write back. So by doing this exercise, somebody said 7 cycles, somebody said 8 cycles, somebody said 10 cycles. From here, I think it is clear which one is the correct answer. So in our assignment and examination also, it gives like this. You need to do this step-by-step process and find how many number of cycles are required for this. How many number of cycles are required for this? Okay. So let me give one more instruction, the set of instruction for the exercise. Let us see what's the right answer comes. Now for instruction 1, it is suppose R1, R2, your R3, add your R4, your R1, sorry, R4, R5, your R6, add your R7, R4, and R8. You will add R9, R10, R11. So for these instructions, can you find out how many, these 4 instructions will execute in how many cycles? Your instruction 1, instruction 2, instruction 3, instruction 4. Your instruction 1 and instruction 2, there is no true dependency, so they can directly execute. But whereas your instruction 3 is depending on instruction 2. I need everyone to give the answer in chat box. So let us see this. The first, I'll write 1, 2, 3, and 4 instructions in cycle 1. In the first cycle, your first instruction will get into instruction fetching, and in the second cycle, your first instruction will be in the instruction decoding, and your second instruction will be in your instruction fetching. In the third cycle, your instruction 1 will enter into your execution. Your instruction 2 will enter into your instruction decoding. In that case, your instruction fetching is free, so that will alert your instruction 3. Now in the second instruction, it is not depending upon your first instruction. So your first instruction goes to the next stage, that is your memory. Second instruction enters into your execution. Third instruction enters into your decoding, instruction decoding. Then at the fourth cycle, it is the fourth instruction will get into your instruction fetching. Now at the fifth cycle, your first instruction goes to your write back. Second instruction goes into your memory access. And what about this third instruction? Your third instruction is depending upon the R4 is this read value depends on the write value. So write after read. So automatically your third instruction at the fifth cycle, it will goes into stall. So when the third instruction is stalled, your fourth instruction cannot enter into your instruction decoding phase, so it will also stop automatically. Then in the sixth cycle, your second instruction will get go into your write back stage. So at this stage, the write operation is going on. The write operation is going on in R4. So your third instruction is also stalls here. When it stalls, automatically its subsequent instruction will also stall. So at the seventh cycle, in the sixth cycle, the write back happens. So in the seventh cycle, your instruction 3 will get the data in the instruction decoding, and it will enter into your execution phase. So in the fourth cycle, when the third instruction entered into execution stall, fourth instruction will get into the instruction decoding. So in the eighth one, your third instruction will get into your memory, and your fourth one get into your execution mode. In the ninth cycle, it get into your write back, and your fourth will get into your memory. At the 10th cycle, your fourth will enter into your write back stage. So by doing the practice, it will give you, we need to identify which instructions are depending. I still think they all take 10 again. Yes, but it is that not the question. Okay, well, I'm honestly struggling to follow, so I'm sure my answers will be wrong. So for 4 instructions, it will take the 10 cycles for this example. Now let us go with the next part. In the stall pipelining, the downside of the stalling is obviously the longer execution time, because by stopping the execution of the instruction, it takes longer time. For example, for the following 4 instructions, in these 4 instructions, stalling the pipeline or prolongs the execution time from 8 cycles to your 10 cycles. 8 cycles to your 10 cycles by entering these bubbles. Or bubbles, sometimes we call these stalls as your bubbles. Okay, so given that applications have a lot of internal dependencies, this performance penalty can be quite serious. So the advantage of these stallings are it is easy and low cost to implement and can solve nearly all pipelining hazards. It may be your data hazards, it may be your structural hazard, it may be your control hazards. but stalling is the last solution to any hazards that cannot solved by other solutions. So this is, the example of, the various instructions. Yeah, the right answer is 10. The cycles will be taken to execute these instructions. Okay. So next comes to the another solution is the bypass or forwarding of this, the right hazards. So bypass or your forwarding means you just recall that we have 5 stages. We have 5 stages. So in the first stage, your instruction fetching stage, we are having the inter stage buffers. So whatever the program counter value and your instruction memory fetching is there, that will come and store into this buffer. Program counter and your instruction memory is there. In the second stage, it is divided, it is also having another buffer in the instruction, it is in the instruction fetching. Okay, this interstage buffer, and in the instruction decoding, you are going to having the register file, and the output of register file will go and store in interstage buffer. And in the execution phase, you are having the ALU to do the mathematical operations, and the result of ALU will again go and store in your interstage buffer. And in the memory, in the memory unit, you will have the memory part, and finally in write back stage you're going to have the register file again. So what it says, bypass and forwarding in this case for these 4 instructions. First instruction, in the first cycle, first instruction will be taken, and in the second cycle, second instruction will be in the instruction fetch, and third instruction, the first instruction is in the decode phase. In the third cycle, first instruction is in the execution stage. So here there is a dependency. So all these are right after. So read after the write of your first instruction. So what happens in the instruction 1 after this execution, after the third cycle, at the end of the third cycle in the execution, the calculated data is ready for your R3. So that calculated data at this execution stage, your R3 data is ready. R3 value is ready, and that value is stored in this inter buffer. So this inter buffer value, okay, that will be used for forwarding its adjacent cycles. It may goes in this direction as well as in this direction. Okay, any unit can access that one. So in the second solution for this, write back hazard is that value goes on for your first instruction execution to next stages. It will be goes on, that is forwarding, bypassing, and this value will be utilized by your second instruction at the end of your third cycle. So that will remove the stalling process. Okay, at the end of your third cycle, first instruction result will, from this interstage buffer, it will be utilized by this instruction to execute. The same value is forwarded to write back in that register. So at the end of fourth cycle, your instruction 2 is executed. So that executed value stores again in the interstage buffer, execution buffer, and that can be utilized to execute the third instruction. And at the fifth cycle, at the end of the fifth cycle, that executed value can be updated. But as soon as that value is forwarding from third cycle to the next cycles, when it reach to the end of, half the way of your 5 cycle, R3 will be getting ready. R3 will be getting ready in the register file. So after that value is getting ready in register file, then they can directly access from the register file. But before R3 is written, in before that the interstage buffer is storing, the value is in the interstage buffer that can be utilized by the upcoming instructions. So by in that way you can remove the stalls and you can reduce the number of cycles, but it is very difficult to implement. So data is usually ready at the end of your execution, at the end of your execution or the memory stages. So basic idea is add some comparator for each combination of your destination. Compare the combination of your destination and your source registers that can have the read after write hazards. So by adding some maxes means your interstage buffers to your data path to select the proper value instead of your register file, the forward data are from interstage registers, interstage register. So bypassing the execution of your first instruction, your memory execution stage and write back, the value is forwarded to the next instruction, forward to the next instruction to execute. So that is bypass and forward. So only stall when absolutely is required. But the difficulty is it is going to have more hardware component parts. So this is another one, and the solution for this in bypassing is we can start forwarding the values of your R3 at the end of your cycle 3 to the instruction 2 and instruction 3. At this cycle, the R3 value can be forwarded to your instruction 2 and instruction 3, but the no negative impact on the performance. In this example, it still takes your 8 cycles to execute the 4 instruction, but disadvantage is fairly complex, change to the control unit and other pipeline resources, and it cannot solve all the read after write hazards. Like forwarding is only doable when the value is ready, right? So with this, uh, uh, another if there are the memory instructions are there for load use hazards with the data, unfortunately we cannot forward back in time because we know that in this third cycle, up to third cycle, the execution is happened, but if there is a load means the effective address will be calculated after this execution, and that effective address, the effective address will be used at cycle 4. So that value cannot send back to the next instruction. It cannot forward that value to the next instruction because it will leads to some other problems. So the pipeline must be stalled to handle these kind of instruction. In the instruction 1, you are having the memory instruction. So the value of your R2 will go and store into your R3. The address of your R2 go and store in your R3, and that R3 will be used by your instruction 2. But for this, the R3 value after third cycle cannot be used for executing that one. If it executes, then that will give the error, the wrong value will be there. So in that case, if this load use is there, then definitely it requires the stalling of your second instruction. When second instruction stalls, automatically the next sequence of your instructions will also stops. So when this second instruction is executed means once the fourth cycle is complete, then that value after fourth cycle, that value will be used from the interstage buffer, before it is going to write back and to calculate the to execute the second instruction So these are the solutions for your the hazards. And another one is instruction scheduling. instruction scheduling or instruction reordering will also reduce the number of cycles to execute. So alternatively, we can remove the bubbles or avoid the stalling by rearranging the instructions. In that case, if in this example, your second instruction is depending upon your first instruction. If you reorder this, suppose if you reorder this, take this second instruction into third place and third instruction into second place, in that case, it can reduce the by rescheduling that one, the first instruction will be executed at the fourth stage. So if this second instruction is executed after third, then at the third cycle, second instruction will be taken into execution, pipeline execution. In the fourth cycle, it will decode. By the time it decodes, your interstage buffer of your memory of your first instruction is ready with the value, which is the effective address, which is calculated here. That will be utilized by your instruction 2 to execute. So that will reduce one cycle. So both the compiler and your CPU can perform instruction scheduling, but for compilers, it is more challenging to identify the opportunities of your instruction scheduling due to unknown memory addresses at compilation time. So the CPU can perform dynamic instruction scheduling with out of order execution. We have seen this, that out of order executions. So the other data hazards like write after read and write after write, these hazards can't happen in your 5-stage pipelining because the order of the instruction is always strictly followed. So, but they may happen when the order of instructions are changed, like changed in your in out of order execution, or if the stages requires a different execution time, and when some instructions have the cache misses. When we talk about this cache design, we talk about this cache misses. So nonetheless, the war and your the write after read and write after write can also be handled using stalls and forwarding. So what about this read after read? That will also happens like right after write time. So with this, I would like to stop this session. With this, I would like to stop this session.